Today and tomorrow from lesson 94, we're going to be discussing this brand new idea for us, which is called the law of sines. Now, before we begin this video, I need you to get your calculator for me, and I need us to check something to make sure that your calculator is in the right mode. If the problem that I give you does not give you the answer that I'm going to state here in a second, then you need to contact me before you continue to watch this video, because I need to help you get your calculator switched to the proper mode. Otherwise, you're not going to be able to answer any of these questions that we're going to walk through together. What I would like you to type in for me is sine. That was the button that said SIN. So sine 30, and then hit your equal button. If you correctly type that question, and if your calculator is in the right mode, your calculator should give you the answer. Either the decimal would be 0.5, or if it gives you a fraction, it is going to be 1/2. If it doesn't say that again, you need to contact me right away because you're not in the right mode and you're going to miss all of these questions. So please make sure that you can get sine 30 is equal to 1/2 or 0.5. Let's go ahead and see what we're going to look at with this idea of the law of sines. What we're focused on are triangles. Now, when we've talked about triangles before and we had to find missing pieces, well, that's the same thing that we're going to do today in our lesson. We have to find missing parts of a triangle. Well, the kind of triangles that we've talked about before were right triangles, something that had a right angle. We had two legs, and then you also had the hypotenuse. We've learned about 3 different trig ratios. We've learned that sine was opposite over hypotenuse. We've learned that cosine is adjacent over hypotenuse, and that tangent is opposite over adjacent. Now, those 3 ratios that we've learned before from sine, cosine, and tangent only apply to right triangles because they involve the hypotenuse. What we're going to notice today, we can actually use trig on any kind of triangle. It doesn't have to be a right triangle, but I can't use our same definitions of sine, cosine, and tangent because I no longer have a hypotenuse in our question. Let me go ahead and show you what is this law of sines that we're going to use in our lesson today. Now, if you'll please go ahead and write this down. I know it looks scary. I know there's a lot of new information, but listen carefully with me. So if you need to, pause the screen, jot this all down, and then come back so you can hear what I'm going to say. The law of sines involves 3 different ratios. You would only use 2 of them at a time when you go to solve in the question. Notice in the triangle, we have 6 different pieces that have letters located on them. And how they're labeled is going to be a big difference in the question. Notice we have 3 capital letters, A, B, and C. Notice where those capital letters are at. They're the angles. You're always going to use capital letters when it comes to angles in our problem. Other 3 letters that I see in this question are lowercase a, b, and c. The same 3 letters, but these are lowercase letters. Where do I notice the lowercase letters are? They're referring to the sides that we have in the triangle. So capital letters always refer to angles. Lowercase letters always refer to sides. That's going to be a big difference as we're looking at our lesson today. Another thing that I wanted to point out about the picture before I kind of explain this law of sines to us, notice the location of the letters that are the same. Well, over here is capital letter A. Then if I go across the triangle, I run into little letter a. Remember, sine was opposite over hypotenuse, so I still want to kind of use that idea of opposite or across from. So my capital letter A is across from lower letter a in my question. Capital letter B is across from lower letter B in my question. And our last letter combination, capital letter C, is across or opposite from little letter c in our question. So again, that makes a difference with where the letters are located. The capital letter is always opposite or across from the same little letter that we have in our question. Let's go ahead and look back at the ratios that we wrote down for our law of sines. What do we have in our ratio? The first one says little a. Remember, little a is a side length over sine capital A. Capital A referred to an angle, and that makes sense because remember when we talked about trig, as soon as we picked any of our trig ratios, what came right behind it was an angle, and the capital letter A refers to an angle. So how did I set up that ratio? It was the side over its matching angle or its opposite angle, and in front of the angle is going to be our sine ratio. The same thing is true about the other two. On the second one, I have little letter b, which is a side length, over capital letter B, which is the angle. Because we're talking about the angle, then we're going to use the sine. So the sine of capital B. The last ratio, little letter c, which is a side length, over capital letter C, which is an angle. Because we're talking about the angle, then you're going to have the sine in the problem. So each one of the ratios, each one of the fractions that we have in our question puts a side length over its matching angle, its opposite angle, and then in front of the angle, we're always going to put the sine because we're talking about the law of sines in our question. Now, one thing I want to point out before I continue in the lesson here, it's really irrelevant whether the sides are on the top or if the sides are on the bottom. What I do need to be careful of is that I'm consistent all the way across the question. The way that I've set up the problem here, all of the sides are on the top and all of the angles are on the bottom. But I could flip those all around. I could put all of the angles on the top, which means all of the sines would be on the top, and then all of the side lengths on the bottom. Again, I have to be consistent. So let's just stay with this one, that all of the sides are on the top and all of the angles are on the bottom of the question. Now, in order to use this idea of our law of sines in the question, you must have one complete ratio. What does that mean? That you have to have one complete ratio. You must have a side length and you must have its opposite or its matching angle. One of those fractions must be completely filled in if you're going to correctly use the law of sines in our question. Now, as I mentioned a few minutes ago, yes, the law of sines does have three different ratios because there's three different side lengths and three different angles that you have in a triangle. However, as you're going to use the law of sines, you would only use two of them at once in your question. One of the fractions you would use is the one that I'm just mentioning, the complete ratio of the side and its matching angle. The second fraction will have one missing piece. Either you're going to be missing a side or you're going to be missing its matching angles. Well, how do we solve when two fractions are equal to each other? We know how to do that. We would cross multiply, and we'll use the same process to help us in our lesson today. Let's go ahead and use the following picture. We're actually going to use this picture to answer the next couple questions. So go ahead and draw this picture out for me, and then we'll walk through what we're going to do on this problem. The first question that we need to answer is finding the length of side AC. And it tells me in the instructions to round my answer to the nearest hundredth, which means I have two decimal places, or two numbers to the right of my decimal point. Well, here in our question is side AC. That's what I'm looking for in the problem. If I'm going to know side AC, or if I need to find that, then I'm going to need to know the angle that is opposite this side. Do I know the angle that is opposite AC? If I go across in the picture, I do run into the 77. So there's one of the ratios that we would use, the side that I'm looking for, and its opposite angle. But remember, if you're going to use the law of sines, you have to have a complete set. You got to have a complete ratio, which means you have to have a side and you have to have its opposite angle. Do we have that in the picture? Well, let's check the other pieces. I'm given angle A, and if I go opposite, well, I don't have that side line. So that's not my complete ratio. And over here, I have a side length of 14. And if I go opposite that, well, I don't know that angle either. So I don't have a complete ratio right now in the picture. So that means I'm going to have to figure that out first. We'll look at the picture. What do we see? Well, I know I have a triangle. A triangle is always 180 degrees. In the triangle, I'm already given two of the three angles. So how would I figure out the angle that's at C? Because if I can figure out this angle, then I'm going to have my complete ratio in the question of the side and its opposite angle. Well, in order to figure out angle C, I'm going to take the total of a triangle, which is 180, and I'm going to subtract out the two angles that are already given to me, the 77 as well as the 38. Now, if you wanted to, you could add the 77 and the 38 together first, then subtract from 180. I'm just showing it as two separate subtraction problems from the two angles that are given to me in the problem. When I subtracted, I found out that angle C is 65 degrees. Now, that's not the question that I'm supposed to be answering right now, but I can't answer the question that's given to me if I don't know that angle C is 65 degrees. Again, why did I need to know that? Because if I'm going to use the law of sines, I have to have a complete ratio, and I didn't have one, but I was able to find one by knowing the measurement of angle C. So back in my picture, I'm going to put that 65 degrees that we just came up with in our problem. Now, I just want to stop here for a second because I just thought of something. Well, I have a triangle. Could I just use the Pythagorean theorem to find a missing side? Absolutely not. The Pythagorean theorem only works on right triangles, and these aren't right triangles, so please don't be using the Pythagorean theorem in this lesson. All right, so that was just a side note. Back to our question. My job was to find AC. So if I was looking for side AC, I need to know the angle that was opposite, and I did have that of 77. So there was my first fraction, AC, over the sine of 77. Notice the sine ratio came next to the angle. Equals, and then my second ratio needs to be the complete set that I have. That involves our side length of 14, because we're putting the side lengths on the top, across from its matching angle, so the sine of 65. We have our question set up now that will allow us to solve for AC. How do I solve? When two fractions are equal, as I mentioned a minute ago, we're going to cross multiply. Now, as I do this cross multiplication, we're not going to do a lot on our calculator, actually very little, until the very final step. We don't want to round too early because then we're getting off on the final answer. So this is what I did. I took AC times the sine of 65. Those were across from each other, so those are some of the pieces that I'm going to be able to multiply together. Okay, so I went this direction, then I went the other direction. The sine of 77 times 14. Again, listen carefully. I did not take 14 times 77. The 77 is attached to the sine. It needs to stay attached to the sine as it was. So how did I write that multiplication? I just wrote them side by side. 14 times sine 77. Again, I'm not typing that in my calculator yet because I would have to round here, that I'm going to round later on as well. And I do not want you to do that because you're going to get too far away from the final answer. We have one more step to get our AC by itself. The AC is currently next to the sine of 65. Well, items that are side by side means they're being multiplied together. So how do I cancel a multiplication? I'm going to divide the sine of 65 over in my question. Notice again, I have not done the division. I am not reducing with these numbers, 77 and 65. They need to stay as they are, attached to the sine ratio. So I have 14 sine 77 over sine 65. At this point of the question, the AC is all by itself. And that was the goal for us to figure out what AC is. Now, I want to go ahead and use my calculator to help me calculate what is the answer on this question. Now, something I do want to point out that a few of you will need to do on your calculator, when you go to type in this numerator, 14 times sine 77. When you hit the sine key, it might pop up a parenthesis right here, and then you're going to type in 77. You need to put a close parenthesis behind the 77. If you don't, your calculator is not going to do the right arithmetic problem. It's going to do what you entered, but not what you really want to do in the question. That is where you have to put the parenthesis. Now, if you want to do the same thing in the denominator, you can. You can put parentheses around the 65, but you have to put them into the numerator. That's something that you might want to look out for if you're not getting the correct answer on this question. The proper answer, if you enter that question incorrectly, should be 15.05 for the length of side AC. Again, if you're not getting that, then you need to stop right now, call me, email me, and I'll walk you through what you need to enter onto your calculator to get that correct answer. Let's stay with the same triangle, and now let's see if we can find out the measurement of BC. Well, here's BC in our question. If I'm going to find side BC, then I need to know the angle that it's across from or opposite from it, which I do know, the 38. So there's one of my ratios, BC over the sine of 38. and then equal. Since the first ratio had a variable, the second ratio needs to be my complete set of information, and it's the same complete set of information that we used from the first problem. Our side length of 14, which was matched up with our angle of 65. So 14 over sine 65. The solving process is exactly the same. The BC is going to get multiplied by the sine of 65, and our 14 is going to get multiplied by the sine of 38. Again, I didn't do anything on my calculator. I just wrote BC times sine 65 equals 14 times sine 38. Do not multiply that 14 and 38 together. That is not what the question wants you to do. We're trying to get BC all by itself. So how do I cancel that multiplying by sine 65? I'm going to divide by sine 65. Whatever was necessary on your last question with how you enter that into your calculator, the same thing would be true here again. So if you need to put these parentheses or close the parenthesis after the 38, then if you want to, you could do it in the denominator, but you have to do it in the numerator if your calculator is saying error or domain error or something like that. If you enter this correctly, you should see that side BC is approximately 9.51. Okay, I have one more example that we'll walk through together today. This one starts off with a word problem, then they give us the picture for us to solve. So Jake is building a fence around his triangular garden. I mean, who wouldn't be doing that? And it's going to be represented by the picture that they'll show us. How many unlabeled feet of fencing does he need to complete the side of the fence? So that means one of the sides is missing. That's our job to find that one missing side in our picture. Okay, so here's the picture that they gave to us. Notice in the question, we have this side of 16, we have this side of 14.5, but there's one side that is unlabeled. That is the piece that we are looking for in our question. So I'm going to go ahead and put X right there, since that's what I'm going to need to find in our question. If I need to solve for X, then I need to know the angle that it's across from or opposite, and I do have that. I have the 58. So that'll be one of the ratios that we're going to set up. Since that ratio has a variable, my second ratio needs to have a complete set of numbers, the angle and its opposite side. Do we have a complete ratio already? We do. We have this angle of 42 degrees, and we have the side it's across from 14.5. Since there's already one in the picture, I don't need to find this angle down here and then use this ratio. I mean, I could if I wanted to, but I already have one, so let's use what was given to us in the problem. Let's set up our law of sines. The law of sines puts the side length on the top, then it's a matching angle into the denominator. So I have X over sine 58. There's the one that had my variable, and then here's my complete ratio, the side length of 14.5 over its matching angle, sine 42. Same solving process we just did in those previous two questions. We're going to cross multiply to help us begin to solve for X. So I have X sine 42 is equal to 14.5 sine 58. Again, don't touch your calculator until the very final step. To get X by itself, divide over your sine 42. That cancels the multiplication. So 14.5 sine 58 divided by sine 42. Whatever you've had to do on your calculator is the same thing you want to do right here. So most of you, maybe it's just entering in these parentheses right here around the 58, and you should come up with that. Jake needs 18.38 feet of fencing in order to complete his triangular fence around his garden. So we begin to look at the law of sines today. The law of sines is allowing us to find missing pieces in a triangle that is not a right triangle. The law of sines matches a side length with its opposite angles. One of those ratios must be completely filled in. The second ratio is going to be where your variable is located, and then we cross multiply. In our lesson so far, all that we have found are side lengths. We've always found the side AC or side BC, and here we found side X. In our lesson tomorrow, we have the side length, but we don't have the opposite angle, and we'll see how do we use the law of sines to find angles if we do have the side lengths.